Hello, dear candidates, and welcome once more to Maths 24 Super Channel and the GCE Maths Panel online preparatory classes. In this lesson, we are looking at the domain of functions. The domain of functions. And please stay tuned to the end of this lesson. Leave your likes and give us a thumbs up. Don't forget to subscribe as you go through this lesson and share this idea with your friends. You can equally join our online preparations by going to GCE Maths Panel classes online and clicking on the WhatsApp link and join thousands of students who are preparing for the GCE and other exams. Please watch this video to the end. So in this lesson, guys, we are looking at the domain of a function. The domain of definition of a function, as it is also called, is the set of all values of x for which the function is defined or makes sense or is not equal to infinity. When the value of a function is equal to infinity, we say it does not make sense and the function is not defined. We will look at the domain of polynomial, rational, radical, exponential, logarithmic, and composite functions in this lesson. You have to pay attention and be very much focused. So if f of x is equal to infinity, what does this mean? It means this function is not defined at this particular value of x and does not make sense because infinity is not a number. It just describes how big the item is. So in this case, the function is undefined or makes no sense at this value of x. Let's look at the domain of polynomial functions. That's where we begin. So a polynomial function, as you have seen in the previous lesson, is a function which has just ax squared plus bx plus c equals 0 or ax cubed, all of that. Those are examples of polynomial functions. And these functions are defined for all values of x. For polynomial functions, the domain of definition is a set of all real numbers. For example, look at the function f of x is equal to x squared minus 4x plus 5. No matter what the value of x is, this function is still defined. Therefore, the domain of definition is a set of all real numbers. Equally for g of x, the domain of definition is a set of all real numbers because no matter the value of x, this function is meaningful, it makes sense, or is defined. Equally for h of x equals x cubed minus 4x squared plus 3x minus 5 and 4. This is a constant. So this is a polynomial function. All these functions have their domain given by domain of f if the function is f, or domain of g if it's g, or domain of h if it's h, is equal to the set of all real numbers. The set of real numbers. You can equally write this in interval notation as domain of definition of f is equal to from negative infinity to positive infinity. Take note of these capital brackets. Look at it. Look at how the brackets are. And look at this other one at the end. They are facing outside or outwards. So this is how it must be. Whenever you see it like this, means this value at this point is not included in this boundary, and this value at this point is not included at this boundary. Students always say in my class that this number is not inside the house because they consider this inside side of it, the inside of the house. So if you was facing this direction, as we are going to see in some examples, then we see how we are going to give the domain of definition. So the domain of definition has two boundaries. Now, in this interval form, we have two boundaries. These intervals or these lines or these boundaries tells us number of bounds. So this is a boundary. This is another boundary. So this one has two bounds. You can clearly see it there, but not here. So that's it for polynomial functions. For rational function, a rational function is a fraction with a variable in its denominator. So a function that we consider to be a rational function is a function that has a denominator, and in that denominator, we should have x there, since we mostly use x as the variable. So if there is no x in the denominator, then it's not a rational function. It should be a polynomial function. So in this case, for a rational function, we get its domain. This is what we do. The first thing to do is we inequate the denominator to 0 because the denominator should not be equal to 0. So we inequate the denominator to 0. Secondly, we solve for x and we exclude this value of x from the set of the real numbers. So first of all, inequate the denominator to 0, solve for x, and exclude this value of x from the set of real numbers. Let's take an example to understand this concept better. So determine the domain of definition of the following functions. The first one, you have f of x is equal to x squared minus 4x plus 5. The first thing is, this function is a rational function. Why? It has a denominator. And secondly, there is x in that denominator. That qualifies this function to be a rational function. So since this is a rational function, we will inequate this denominator to 0, like this. We solve x, and we remove it from the set of real numbers. So we have x minus 3 should not be equal to 0. Because if x minus 3 is equal to 0, this denominator will be equal to 0, and anything divided by 0 is undefined. This function will be undefined if x is equal to 3. So when we solve x should not be equal to 3. If x is equal to 3, this function will not be defined. So we write our domain as follows: the set of all real numbers excluding 3, or we can write it in this form. In interval form, we have from negative infinity. Can you see? Negative infinity is not included, to 3 from below. 3 is not included because it's outside the house. And then it continues from 3 from above to positive infinity. So you have from negative infinity to 3 from below, and from 3 from above to positive infinity. When you write it like this, 3 is not included. We are going to see a case where the 3 can be included. That is when you get to radical functions or root functions. So the last way to write this is to write like this: a set of all real numbers minus or excluding 3. This one is mostly asked for technical school students. And this one is very good because you can tell the number of bounds in this function. The number of bounds, we have this: the first bound, 1. This is another bound, 2. This is another bound, 3. Another bound, 4. In fact, you can count the number of these brackets that you have like this. This is 1, this is 2, this is 3, and this is 4. So it has 4 bounds. This is very important because if they ask you to look for the limit at the boundaries or at the bounds of the domain, then you have to look for 4 limits. We can combine some depending on the type of function that we have. But normally, if you have 4 limits, you can have limit at positive and at positive infinity and minus infinity combined, or we can separate them depending on the type of function. Especially for exponential functions, we can separate them. But for most of these type of functions, we can combine. Now, for this second function, it's a rational function too because there is x in the denominator. So we inequate this denominator to 0. 5 minus 4x should not be equal to 0. Therefore, x should not be equal to 5 on 4. And the domain is a set of all real numbers excluding 5 on 4. So you can write in interval form as from negative infinity to 5 on 4 from below, and then we continue from 5 on 4 from above to positive infinity. So this is the domain of this function. Guys, please don't forget to subscribe to this channel, and secondly, to share this video with all your friends and WhatsApp groups to help especially suffering students to have this material and help prepare them for their exams. Thank you so much, and God bless you as you share. Don't forget to subscribe as you have said. Thank you so much, and watch to the end. So another function that we have here is this one. If you look at this denominator, this is a quadratic denominator, and there is x in the denominator, therefore it's a rational function. So we inequate this denominator to 0. When we factorize this, we'll have x minus 5 into x plus 1, or you can use the quadratic formula, no problem. These are the values you have. X should not be 5 and x should not be equal to minus 1. Because if it has any of these values, then this function will not be defined. And in the other lessons that we'll be looking at in future, these values for which the function is not defined for these functions give us what we call the vertical asymptotes when we'll be looking at asymptotes. So vertical asymptotes are x equals 5. In that case, we don't use inequating. We don't inequate, we equate. So the vertical asymptotes are x equals 5 and x equals minus 1. But since we are looking for domain, this is how we do it. So we have to exclude these two values from the set of real numbers, as you can see. And in interval notation, it's very sweet. From negative infinity to -1 from below, we continue with -1 from below to 5 from below, and 5 from above to positive infinity. And this function has how many bounds? 1, 2, 3, 4, 5, 6. Set of functions are very, very common in BAC and in the former exams that they were writing called probatoire. Exams, very common advanced level. Very, very important for curve sketching. Okay. If you look at this other function here, it may be tempting. Look at this function. This is a temptation. Guys, look at it very well. This is a temptation. Be very careful with this function. If you look at this denominator, you have to equate to 0, right? If you do that, you are wrong. Why? Because no matter the value of x in this function will still be defined. Look at the denominator. No matter the value of x that I put in the denominator, it will never be equal to 0. This denominator can never be equal to 0. Put any value here, square it and add 1. You will never have 0 as denominator. Therefore, this function is having a domain of definition, the set of all real numbers. Be very careful with this one, as I've said. As you can see, the denominator is always greater than or equal to 0. The smallest value the denominator can take is when x is 0. And if x is equal to 0, the denominator will be equal to 1. So the smallest value is 1. Thus, the domain is the set of all real numbers from negative infinity to positive infinity. Now we are looking at radical functions. And a radical function means it's a function that has a root in it. And here we are focused on square roots. So normally for a square root of 0 exists. So we are going to consider those concepts. And so a radical function, if it has a denominator, which is a variable, just like the previous one, a rational function, we are going to follow those principles as well. We are going to see all those examples here. And we'll exclude that from the set of real numbers. Don't worry about the grammar so much. You will see that in the examples we are going to solve. Example 3, determine the domain of the functions below. Here we're looking at radical. Radical means roots, like square roots, which we have just mentioned. So if you have h of x equals 3 minus x, now for this type of function, for root functions, what we have inside the square root sign should be greater than or equal to 0. If it's equal to 0, it will be defined because the square root of 0 exists. If it's greater than 0, it will still be defined. Note, we don't have the square root of negative numbers when we are talking about the domain of definition of a function. The square root of negative numbers don't exist in the domain of definition of functions. Take note of that. So the condition here is that for this type of root function, this core or this 3 minus x must be greater than or equal to 0. Therefore, when you solve this inequality, x should be less than or equal to 3. If you don't know how we solve this, please go to chapter 1. You have chapter 1a up to E in this pure mathematics series, season 1. Season 1 is pure maths. In season 2, we'll be looking at statistics, and in season 3, we have mechanics. So we are still in season 1. Please watch this season as you watch other series in the house. But I say the domain of definition here should be the set of all real numbers, excluding x less than or equal to 3. No, excluding x is strictly less than 3 because we already have this, right? So this function is defined if x is strictly less than or equal to 3. So it therefore means it's going to be undefined if x is greater than 3. We have to be very careful. I have said all of these things because these are the things that the students said in class and some of the mistakes that they make. So this function is not defined whenever x is greater than 3. So the domain is a set of all real numbers. X is such that x is less than or equal to 3. Any number less than 3, you put in this function, it will be defined. But if any number greater than 3, this function is not defined. So you can equally write the domain like this, set of all real numbers, excluding the set for which x is greater than 3. Here we have x is such that x is less than or equal to 3. Here, set of all real numbers excluding the set such that x is greater than 3. And in interval form, we just have from what? From negative infinity to 3 because the highest value is 3. Now take note of this point here. Can you see this blinking arrow? 3 is included in this domain of definition because look at it here, we have less than or equal to. So x can be 3. If you put 3 here, I have 3 minus 3 is 0. The square root of 0 exists. So 3 is included. Consider 3 is inside the house. But negative infinity is not. So 3 is inside the house. 3 is included in this domain of definition. So it's included in this boundary. Then we have this function x minus 2 over x plus 1. So with this function, this is a radical function, that is root function, and it also has a rational function inside. So we are going to combine all of those conditions. So this one has conditions that this core inside this root must be greater than or equal to 0. Another condition is that the denominator should not be equal to 0, because if this denominator is equal to 0, this function inside will be undefined. So this core, firstly, should be greater than or equal to 0. And another condition is that the denominator should not be equal to 0. The numerator can be equal to 0, no problem, because you give us 0 and the square root of 0 exists in this case. So when we to solve this, we can, here f should not be equal to -1. We can make a number line. Since this is a range of values, as you can see, we are going to test. X should not be equal to -1, but x can be equal to 2. Take note. This one mostly happens with root functions. X, that's why we have shaded this one, but this one is open. So we are going to test in these intervals. So we take any number between -1 and 2, 0, for example, and fit here. 0 minus 2 is -2 over 0 plus 1, 1. -2 plus 1 is -2. Is it greater than 0? No, -2 is not greater than 0. So -2, we have -2, which is not greater than 0. What does that tell us? That tells us that this region here does not satisfy. Does not satisfy.